This lecture series is intended to give the audience an understanding of how to use the Insight spreadsheet to develop and deploy machine vision applications. Part 1 will cover fundamentals of how spreadsheets work using Microsoft Excel as an example spreadsheet environment. Part 2 will introduce you to how to build a machine vision application using the Insight spreadsheet. Part 3 will cover some advanced topics that are unique to the Insight spreadsheet, and Part 4 will demonstrate how to incorporate ViDi deep learning tools into an Insight spreadsheet application. There are a lot of definitions of the term computer program, but stated in a simple way, a computer program is just a list of instructions that tell a computer what to do. I want you to close your eyes for 5 seconds and create a mental picture of what you think a computer program looks like. Okay, open your eyes. I'm guessing for most of you, a computer program looks something like this. A list of instructions using a syntax like C++ or JavaScript. This is a perfectly good example of a computer program. But this image is also an example of a computer program. I'm not talking about the product Microsoft Excel being an example of a computer program developed by software engineers at Microsoft, but rather the contents of the individual cells that make up a spreadsheet inside the Excel application. When we create something like a sales report in Excel, we're actually writing a computer program. Long before there were computers and spreadsheets, we learned to do basic math, like multiplication, in grade school. And then along came affordable calculators, and we retrained our brains to do simple data entry, and the days of using pencils and paper went away. But what is a calculator? It's really just a small computer that's been programmed to perform mathematical calculations. But a calculator doesn't do anything until a person enters data and an expression. So in a way, when we enter a number followed by a mathematical symbol, followed by another number, then press the equals key, we're using a syntax to describe the expression we want to solve. We are, in a sense, writing a computer program. And thankfully, the syntax employed by early Hewlett-Packard calculators, something called reverse Polish notation, has largely gone obsolete. If we extend the metaphor of combining data with a syntax for processing into a spreadsheet environment, what we have is the ability to write much more sophisticated programs than we can write with a simple calculator. An individual cell can be a piece of data. That data can be of different data types, like integers, floating point numbers, strings, or even functions that return a result back into the cell. And we can pass data from one cell in the spreadsheet to another cell by using what's called cell referencing. The cell name, denoted by its column row location, is in programming lexicon the name of a variable. Spreadsheets provide a large collection of library functions we can insert into cells. If we happen to know the name and syntax for a function, we can simply type it into a cell. But if we don't know exactly what we want to do, we can search through the function table, which is organized by categories. When we click on a function, we see a brief explanation of what that function does. If we need help with understanding what individual parameters of a function mean, something called a property sheet can be used to enter values and get a brief description of each parameter. We can enter data directly into the property sheet, or we can use a cell reference to point to data that exists somewhere else in the spreadsheet. In this case, cell B2 is used as the input to the parameter called find text. Now let's look at an example we're all familiar with, a typical sales report. Imagine having to add up all of the totals using a calculator. We'd need to enter each month's value, and chances are we'd make a mistake with the data entry and have to start over. With a spreadsheet, we can replace the data values with cell references, and Excel is kind enough to provide a sum function that uses a special syntax, in this case B3:M3, that will collect all of the data points in row 3 from column B to M and compute the result. And if we copy the function in cell N3 and paste it into cell N4, the spreadsheet is smart enough to automatically modify the input cell references to use the corresponding row of data for the new function. When we paste down one row, all input arguments are adjusted one row down also, in this case B4 to M4. On the previous slide, we saw what happens when you copy and paste a cell using what's called a relative reference. Normally this is pretty handy, but there are cases where we don't want the cell reference to change when we copy and paste a cell. We can do this using what's called absolute referencing by inserting a $sign before the row and column name. Let's take a look at where we might want to use absolute referencing. In this example, I want to build a table to calculate loan interest payments for different loan durations and different interest rates. If I were to use relative references in my PMT formula and point to my loan amount in B11, the duration in C11, and interest rate in B12, then paste this function into other cells in my table, my calculation will be meaningless. Here I copy the function in C12 to D13, which is over one column and down one row, so each cell reference in the original function is increased one column and one row during the paste operation, meaning they're no longer pointing to the desired source data. Absolute referencing is a way to lock the column, row, or both column and row of a cell reference. $B12 locks the column only during paste operations. So as I paste the function in other cells, I will still reference the column containing the interest rate values. $11 locks only the row during paste operations. So as I paste to other locations, the function will retain the link to the month data. And $B$11 locks both the column and row. So no matter where I paste the function, it will retain a reference to the loan amount cell. Here you can see the resulting paste operation, which retains all of the proper source data cell references. As we add spreadsheet functions, two common questions often come up. First, what causes a spreadsheet to run? And second, in what order do cells execute? Spreadsheets are what we call event-driven. Some sort of change or stimulus is required, and then the spreadsheet automatically updates. Change could be in the form of adding a new function, changing data in an existing cell, or it could be from some external event, such as another application writing data into a cell. As far as execution order, the order is completely independent from cell position. Unlike a traditional computer program, where execution order is sequential from top to bottom of a program, spreadsheet cells only update when they have to, and the order is completely controlled by the execution engine, which manages something called the dependency tree. Here are two examples of dependency trees. On the left, it's pretty straightforward to see how changes ripple through a dependency tree. If we change the label in cell F1, nothing else happens. But if we change a value in cell B1, this change means that cell C1 and C2 will update, which in turn causes cell D1 to update also. The dependency tree on the right is a bit more complex. If we change the data in cell C20, the change will propagate through all of the cells that are connected automatically. Notice cell D10 near the bottom has two inputs. In this case, it will only update after cells F18 and H8 have both been updated. In other words, the cell update of F18 doesn't immediately cause the update of cells D10 and D30. That's because the dependency tree is efficient, and we'll see the significance of this even more when we get to the Insight spreadsheet. One last thing to note about the dependency tree is something called circular references, as shown by the red arrow here. You can probably see, for obvious reasons, that cell E1 can't become a dependency for a cell elsewhere in the tree that depends on cell E1. This would, in effect, create an infinite loop where E1 updates E2, which updates H8, which in turn updates E1 again, and round we go. If you attempt to enter data into a cell that creates a circular reference, the condition is detected as an error and must be corrected immediately. If we go back to our sales report example, let's see what happens if we need to update the November data for the South region. Here we have two cells consuming that data. Cell L7 computes the monthly total, and cell N4 computes the region total. And after cells L7 and N4 update, cell N7, which computes the overall total, also needs to update. Within Excel, there is a menu option that prevents automatic cell updating. This could be useful if you have a function that takes a very long time to execute, say something like a query to a large database, which has several input cell dependencies. Setting cell updates to manual prevents all cells from updating until you click on each individual cell. Since this setting is global, it can be easy to forget it's enabled, so use this feature with caution. In summary, let's take a brief look at what we have learned. For many of you, these lessons may be things you already knew, but grounding ourselves in the fundamental behavior of a spreadsheet is really important as we move towards using a spreadsheet as a development environment for building a vision application. I think we can all agree that calculators, while handy, are not practical for building something as straightforward as a sales report. More traditional programming methodologies, like C++ or JavaScript, are very powerful, but pretty complex unless you're trained as a software developer. Finally, a spreadsheet is just another paradigm for programming a computer, and the magic of the dependency tree frees us up as application developers to focus on solving our problem. Coming up next in part 2 of this lecture series, we will learn how to use the basic principles of spreadsheet programming to build a machine vision application. Thank you for watching.